Good day everyone. Today we're going to talk about diffraction grating. So what exactly is this diffraction grating? So a diffraction grating is defined as an optical component with a periodic structure that splits the light into various beams that travel in different directions. It is an alternative way to observe spectra other than a prism. It is an interesting thing that happens if light passes through a large number of evenly spaced parallel slits, and then the interference pattern is created that is very similar to one formed by double slit diffraction. So these gratings work both for transmission of light and for reflection of light, like in a CD. Now let's take a look closer in a CD. You may think you can see the grooves in it because you know they are there, but actually they are extremely narrow, about 1600 in millimeter. Because the width of the groove is similar to wavelengths of visible light, they form a diffraction grating. This is why you can see a rainbow on a CD. The colors are attractive, but they are incidental to the functions of storing and retrieving audio and other data.
Now, let's elaborate further the grating relationship by using the formula d sine theta equals n multiplied by lambda, where d is the distance between the slits, theta is the angle of diffraction, lambda is the wavelength of the light, and n is the order of diffraction.
Consider a magnified view part of a diffraction grating. Each slit diffracts the light waves that pass through it. The diffracted waves then interfere with each other. Where crests meet or trough meets, there is reinforcement. This is what we call constructive interference. And where a crest and trough meet, there is cancellation. This is what we call destructive interference. This results in only the orders of light being viewed.
Now let's apply the diffraction grating formula in simple calculations. So we have a problem here. A diffraction grating has 600 lines per millimeter. If such a grating is illuminated with yellow light at 6 times 10 to the power of -7 meters, calculate the angle at which first and second order diffraction will be observed. Now we have a diagram here that shows the light passing through the grating. And remember guys, zero order of diffraction is always at 0 degree to the normal. Take note that the spacing of the lines or distance is 1/600,000 millimeters. Now we will use the formula n times lambda equals to distance times sine theta. Since we are looking for the angle, we will derive the original formula into this formula as shown in the screen, and then we'll just substitute the given. So the angle on the first order diffraction is 21.1 degree. Now, in finding the angle of second order diffraction, we'll just change the n into 2 and then substitute the given. So the angle in second order diffraction is 46.1 degree.
In addition to their use as novelty items, diffraction gratings are commonly used for spectroscopic dispersion and analysis of light. What makes them particularly useful is the fact that they form a sharper pattern than double slits. That is, their bright regions are narrower and brighter, while their dark regions are way more darker than one that forms in the double slit. Shown in the screen is an idealized graph demonstrating the sharper pattern of a diffraction gratings compared to a double slit.